normally dinner talks are meant to sort of be humorous. We're actually going to dive in, well, to hopefully have a little bit of fun, but we're going to dive in and talk about some of the big changes that are happening and how that is different maybe from classical computer science, things that we've been learning for a very long time. So computing has actually, HPC computing has been pretty successful. We have a number of very large deployed machines around the world. You saw that President Obama just signed a sort of an initiative. Of course, now Congress has to pass legislation to fund things, but there is intent that HPC computing is very important for the nation, and that simulation and modeling is very important to key science areas and key ways that, that the US is competitive. So we've been doing pretty well, and so sometimes you hear all of these talks about Exascale, and maybe you start to wonder, well, you know, we're doing pretty well. Is there really anything different, anything to worry about? Why do we, you know, say that something is that Exascale is so different? And we heard from David a lot of the examples, and I'll actually be leveraging some of those concepts as we talk. But really, I do believe things are a-changing. And for those of you who are maybe understand the history here, so Bob Dylan in about 1965 went to a folk festival, and he brought an electric guitar. And this was just a complete change since he had been known for acoustic guitars, but also the very idea that electric guitar could even possibly produce you know, music, beautiful music. But he understood that that is the path, that's where things were going, and even though he got booed initially, eventually it caught on, and everyone at that time started using electric guitars. So we're in a phase where we are switching from a kind of manual way in which we program things, and David pointed out some of these things with dynamic programming and the very static nature of our machine, to a changing time where things are going to be different. So I'm going to lay out, point out three areas where our classic understanding is now going to be supplanted with this new understanding. So the first old wisdom is Moore's law, that we get these great free speed-ups. Now, what's kind of fun about this is if you've been watching in the newspapers, this was a Wall Street Journal article. I was on a plane to Edinburgh, and the Wall Street Journal article had this, you know, we're turning 50, Moore's law is turning 50, and gee, you know, companies that can afford to keep pushing Moore's law are finding it increasingly hard to keep the pace. And then immediately after that, Intel comes out and says Moore's law will continue. And this was back in this was in February, and then I don't know if you saw this note a couple weeks ago that said that Intel was delaying their next shrink, right, to the next feature where they would be able to reduce the feature size for the chip. And I really love how one company put a positive spin on that by saying Intel is about to save $1 billion by failing to keep up with Moore's law. So this isn't a bad for Intel stock, it's a good thing, because it means that they're not going to try and spend $1 billion to keep up with Moore's law. But the real thing, the note to take out of this message is that our old wisdom, this exponential that we've lived with for so long, is going away. And you know, the reality is that even over the last few years, since 2004, as was mentioned earlier, we've only been getting about 13% faster every year. Now, Intel chips, as the company, they've done a little bit better in general, and Intel has done about 21% over the same period. But the general architecture, the general speed for most chips is really not increasing at that exponential that we're used to. And this is just a simple example of single core performance over this time period versus the total performance of the socket, this is just a repeat of that statement that really the way we're getting more performance is not by Dennard scaling, not by shrinking and speeding up a clock, but by adding more parallelism. We just keep making dies and cores more parallel. However, we know, this is a kind of an obvious law, but Herbert Stein's law, if something cannot go on forever, it will stop. It's always good to put these things in writing and then maybe get them out first and have something named for you. So we know that Moore's law, even though we hear, oh, it's going to be fine, we know that at some point it has to stop because it can't go on forever. We can't have feature sizes that are smaller than electrons. It's just not going to happen, right? So we are already slowing tremendously, and more importantly, the cost per transistor is not shrinking. So now that's even more important, right? It's not getting smaller. So it used to be with Moore's law that one of the things that would happen is we'd get less, it would be cheaper for the same number of transistors every year. So we would get cheaper transistors. With the size of the die and with the complexity of making these things, that $1 billion that's going to be saved, so the transistors are not significantly cheaper now. So you can make more sophisticated, you might be able to add more cores, but they're not getting tremendously less expensive. So this means that architecture, as mentioned earlier, is going to change how we look at things. And this is a very good example of that. Just kind of, it's always good if you look at a company to see who they're acquiring. It kind of gives you a picture of, in the future, what do they think they have a hole, where do they think they have a hole, and what do they need to do. So recently, Intel noted that they are looking to acquire, and earlier James pointed this out, Altera, who makes FPGAs, for $16 billion. Now now you're talking a lot of money, right? That's real money. That's Apple-sized money, you know. And the point is because once we get to the this sort of leveling off of how much transistors cost, it's how we use them that matters. So having specialized ways in which we put the circuits together, being able to reconfigure hardware for particular problems looks like it's in our future. It might not happen, this will take a while, and it might not happen in the next 5 or 6 years, but we can certainly imagine it happening as we try and push and reduce power. So the first old wisdom is that Moore's law we get for free. That's not true anymore, and it does affect the way we look forward to our programming. The second is that the way we optimize programs and the way we look at our code is we try to minimize the number of ops. So earlier, in fact, was mentioned the sort of the Bible of initial computer programming. If you're a computer science person, is Knuth's The Art of Computer Programming, and of course it starts with book 0, not book 1. And in Knuth's books are sort of classic programs and algorithms, classic algorithms, where you evaluate algorithm A against algorithm B and find worst case, best case, average case. So when I took analysis of algorithms as a student, as a grad student, I mean, we would run through every possible, algorithm, whatever kind of sort or queuing algorithm, and you would do best case, worst case, average case, right? So that you could evaluate the algorithm. However, the problem here is that we all start to understand, okay, bubble sort, quick sort, tournament sort, and we come up with these things, but they're all based on counting ops. Sometimes an algorithm, when you teach an algorithms class, you'll say, well, how much space does the algorithm take? But primarily, we're comparing things by counting ops. And this is the way we've been in high-performance computing as well. We have counted flops. So this old wisdom is that we would explore our algorithm space by looking and comparing and thinking, how do I reduce the number of operations I need to do? Now, more recently, as David pointed out, memory movement and moving data has been something that algorithm designers are looking at. And even back, this is from Guillaume van Loom, even back in 1996, This is a page from the book here from 1996, a very famous matrix book on how to do matrix computations. There's a small bit here about, well, thinking about data motion, that there actually is a cache in main memory, right? So you should think about data motion. But algorithms were still not evaluated based on data motion. And in fact, if I were to ask this group here and say, okay, a homework assignment for tomorrow, evaluate these 3 algorithms based on minimizing data motion, it would be, okay, what metrics do you use? How would you actually do that? Do you minimize total bytes, bytes over time, bytes between different areas of memory? This is still an evolving space for us. So the way in which we come at computer science is changing. We know that it's data movement. And over time, we can look at essentially, this is the picojoules here in the y-axis is the energy, picojoules per 64-bit operation. And this is now looking for across the memory hierarchy. This is a double precision flop right here. And this is 2018, the red. So we'll look at this, 2018. Here's a double precision flop. And it takes a little bit less energy to move it between a register and maybe a millimeter on the chip. But as soon as we get up to moving it a couple millimeters, just moving the data a couple millimeters on the chip is equal in energy cost to a flop. So now we have now we finally have a way in which we can start comparing algorithms and start thinking about things. Wow, now we're talking moving millimeters, right, and comparing that to flops. But as soon as you get all the way up into 15 millimeters or off chip, well, now we're tens or hundreds of times more energy than just doing a flop. So you can see here that trade-off of doing 100 times more flops for reducing where the memory moves by several millimeters could be quite a savings for an algorithm. All right, so this is pretty remarkable. It changes the old wisdom of optimizing for flops. A couple weeks ago, actually exactly about a month ago, I was in Canada, and I went to the airport, rented my car, and I had a particularly new car. You get in, you turn the car on, and the odometer shows like 58 miles or something like that. It was amazing. And so I pull out of the airport, drive off the airport lot, out of the parking lot, and I get to the first stop sign, and the car dies. And I'm thinking, man, 58 miles. And I take my foot off the brake, and the car starts up. How many of you have been in a car like this? All right. Okay, so in the new power-saving vehicle, when you put your foot on the brake, the car turns off. This isn't a Prius. It's not an electric car. This is a standard gas car. And when you shift from accelerator to brake, boom, car turns off. And then you pull your foot off the brake, and you try and very quickly put it over the accelerator to test how fast the car can start and you can move. And it's pretty snappy. Okay? Now, it's not as snappy as if the car had been idling the whole time, right? But it's not bad. So this is a power-saving feature that for the longest time the companies resisted, and now has been added into the control system of the vehicle so that when you stop, car turns off, put the gas on, car turns on. It saves in town the projected number, the current number. This was on a GM, I guess, or a Chevy, was about 14% fuel savings in town. Well, that's pretty remarkable. Okay, now that's for fuel savings. Now, why am I bringing this up in a computer talk? All right, so it's this kind of system that is now in the heart of our CPUs. So what's different about the car is that normally we're used to our pedal, our accelerator and the brake pedal, actually being connected to physical things in the car that I'm adjusting, like the brakes, right? But now, for this to work, there's a fly-by-wire, right? So that when I push on the accelerator, it's actually not adding gas to the engine. It's telling the engine, Pete would like to go faster. And when I put my foot on the brake, it may be telling the car, I want to slow down, and there may be regenerative power harvesting that can take place. Well, that's what's happening now in chips as well. It's been happening for a long time. The power-saving features of the modern CPUs are such that we don't tell it exactly what clock speed to run at or what to do. We give it hints, and the CPU has a control system that's deciding how fast it should run and what kind of operations it should do. So let's look at an example of this. So the classic case that you're familiar with is sort of power saving in a laptop, DVFS. When you're not using the laptop, it might reduce power, reduce the clock. But what we're talking about now is Turbo Boost. So in Turbo Boost, here's a program that we're running where this is the temperature of a system, and we have two sockets in that system. So one is sort of the blue-pink package, and the other is the black-green package. And we're running an intensive program. I think it's a DGEM. And we start this thing up, and you see that the speed, this is the clock speed of package 0 and the clock speed of package 1, and it's 2.6 gigahertz, right? So you see both of them heat up. One of them seems to get a little bit hotter. Depends on the thermal characteristics of the motherboard. Looks good. Now over here, on package 1, it's 2.6 gigahertz, 2.6.01, okay? A fraction of a gigahertz faster. I tell the CPU, that's what I want to set you at. And immediately it does this other crazy thing, right? It goes way up over 80 degrees, then it drops back down, then it goes back up like this. What's happening? At 2.6 epsilon, whenever you go slightly above 2.6, you're triggering the internal control mechanism of the chip to turn on Turbo Boost. That now says, I don't have the accelerator connected to the engine. There's a control system that will do the best it can for me. So it's going to ramp up and put in way more power, and in fact, clock speed, if necessary, than I ask for to give me as much speed as I can. And of course, that's going to overheat the chip. And it's going to go up here, and then the chip is going to realize, oh, I'm too hot. I've got to cool back down. And then it's going to drop down here, and then it's going to find this nice happy medium as it continues on. The point here is that the chips are now designed such that they can't even achieve the highest performance unless you enable the dynamic control system that's inside the chip. And they also can't sustain their highest performance. There's no way that it can sustain its internal, possibly up to 3 gigahertz or something, performance. Some other examples of this here with this sort of, you see this action where it speeds up, slows down, speeds up. The point here is that in modern CPUs, the difference between its sort of base performance and the Turbo Boost performance can be more than a factor of 2. So that turbo performance is not going to last. In other words, it doesn't last for an hour while you do your computation. It's going to heat up the chip for a while, and if you reduce your ops, it's going to come back down. So it's going to be very dynamic. And as this picture shows, up to a factor of 2 in performance on the current chips like this. The latest, especially used in laptops like your laptop and so forth. Then if you look at starting to go even further, you have, of course, the memory hierarchy. So the real reality here that's most important for us is that when we write parallel programs now, we assume equal work is equal time. We divide the program up into chunks. We expect in our head the abstract machine model. Remember this morning when I said, pay attention to the model. Our model is that equal work is equal time, and the program will execute, the computer hardware will execute all the chunks in equal time. That's not the case. So this is our new reality here, where computing rapidly gets faster and cheaper. That's not exactly true. What we have instead is we have this rapid exponential improvement is over, and we have slow improvement, and we're just keep adding parallelism, and we keep squeezing ways. We're going to have special functional units, FPGAs, other things, even more heterogeneous computing in order to try and squeeze performance out of the transistors that we're not getting cheaper. Efficient programs minimize operations. Well, that isn't exactly the truth anymore. Efficient programs minimize data movement, even sort of measuring millimeters, how far the data goes. And finally, computers run at a fixed predictable speed. In your mental model of the computer, that's not true either. The computer is quite flexible. Now, years ago, there were probably, I think it was in 2013, there was a paper where they looked at the top 500 and they looked at all the machines that had turned off this DVFS, which is the ability to save power by changing the clock speed and voltage. And all the top 500 machines had turned that off. Okay? Now, it didn't cost them anything because remember, that's only power savings. However, with Turbo Boost, it's not a power savings question. If you turn Turbo Boost off, then you only get the base CPU, the 2 point, like in that example, the 2.6 gigahertz, and you don't go any faster. So all of the modern computers which have this kind of chip have turned that on. So the NERSC machine, for example, struggled with this. Well, what do we do? Do we turn it on? But then all the nodes can run at different speeds. Now we're going to have some nodes speeding up above 2.6 and some not. Right? This adds dynamic behavior into the mix. So let's look at that in particular. Right now, if you just sort of imagine scalability, you're trying to write your most scalable algorithm. There are really three things that you have to solve to get scalability. One is you have to make sure you have sufficient parallelism. That was mentioned this morning with Amdahl's law, right? And sort of strong scaling is one way to do that. You add parallelism. The other thing you have to do is you have to make sure you hide latency. So if you don't have sufficient latency hiding, then your program is going to have problems speeding, going fast. Finally, you have to make sure you have the right number of resources. I think, just is your program fit in memory? Do you have the bandwidth necessary to do the application? So I'm going to look here at this latency hiding one because the problem here, and it's just going to riff a little bit on this dynamic behavior piece, is that as we scale the machine, it becomes more dynamic. As we squeeze power to make it more power efficient, the machine becomes more dynamic. As we address resilience, the machine becomes more dynamic as we fail parts and automatically do something. And as we share networks, as you heard Pavan this morning, you don't get a network that gives you perfect crossbar connectivity. You have to share it even amongst your own nodes, but also possibly with other users of the system. So our hardware is dynamic and adaptive. And so bulk synchronous, as was mentioned, is our scaling problem. Now, a note, MPI is a library that moves data. MPI doesn't imply that you have to code in a bulk synchronous way. Often people use it in a bulk synchronous way because it's convenient to use that way, but it's not required. And in fact, I'm sure Rusty will point out at least one example that is not using it in a bulk synchronous way with ADLB, right? If there's time. So this idea of OS noise and jitter is really sort of a legacy distraction. Our machines will have some sort of distribution of execution speed. And they have a distribution of execution speed right now. As I said, the NERSC machine and other machines have Turbo Boost turned on. You will notice different times and different speeds on all of the nodes. So the question that we have to ask now as we look forward at this is how much load balancing do we need, and how do we design algorithms that are able to do some of this sort of balancing and be more adaptive, to be more pliable? And can we create tools that measure this, predict, and learn from that so that we're not trying to do it by hand as a human? So now, unfortunately, we're still sort of in this world where we hope that the machine is perfectly static. Now, I'm poking fun a little bit at NERSC here with this, but they recently procured a machine, and in the procurement documents, the document said, the system shall provide correct and consistent runtimes, no more than 3% from run to run. So I don't understand first what a correct runtime is. I guess that means it runs fast or slow. But the thought here, by putting this into a contract, is that the machine is supposed to be static. Now, the machine they bought wasn't static, right? It's not. But we're still stuck on this idea that when I submit a job and it takes 2 hours and 15 minutes, that the next time I run the job it should take 2 hours and 15 minutes plus or minus a couple percent. And that's probably not going to be the case, right? The more dynamic we have, the more dynamic behavior we have, the more likely that has to be something that we're comfortable with and moving around. Furthermore, ASCAC had an Exascale research report that was sort of the challenges of Exascale, and it's great from a computer scientist perspective of low-level system software that all of these challenges, power management, is some sort of dynamic adjustment, enabling dynamic optimizations, and the next generation runtime systems support several classes of dynamic adaptive functionality. Well, so that's job security for me, right? I'm getting to write all the dynamic stuff. But it also points out that if we just look at what we need to do, our system software, and in fact then your algorithms, will need dynamic behavior and will need to respond with runtime systems. So lessons for the future as we sort of wrap up here. So code should be as static as possible. It's kind of an Einsteinism here. As static as possible, but no more so. So obviously your for loop should be your for loop for most of the time, most cases. However, it is worth inspecting now, looking at your application and thinking, well, if equal work is not equal time, how unequal does it need to be before I care? Right? At what point will I need to replace this, and this is what James talked about this morning, with something like Silk, thread building blocks, or we'll talk about something that we're doing at Argonne. Take small steps to becoming more pliable. So you can look at mapping of the resource, of load balancing, dependency graph tiling. These are all things that you can do to take small steps before going completely toward sort of goal-oriented optimization, where you do lightweight, dynamic work balancing in some form. We should also assume that in the future that dynamic behavior is not an error, right? It does not mean that the machine is broken or that the machine is doing the wrong thing. It means the machine is power efficient, is what it really means, right? Okay, so I happen to work on a project that is doing some of these pieces with respect to operating systems and parallel runtime systems. And one of the things that Pavan is working on, so he spoke this morning on MPI, but really another project that Pavan has that's critical is a very, very lightweight threading project called Argobots, and its design is so that lightweight tasks and threads can run, and you could spawn hundreds or thousands of them very easily and have them work to completion in a very, very low overhead way. And in fact, we've been working with the Japanese to have OpenMP back end into very, very lightweight threads like this. So this morning, in fact, James isn't here, is he? He had to fly, right? So this morning, James pointed out that there's a problem with using OpenMP for composing parallel programs, because you specify how much parallelism there is, and he mentioned how the OS will then allocate 4 or some number of P threads, and then if you want to specify it again because you go into a subroutine, what do you do? Do you create, well, my argument is not that you need to not do that or find a workaround in OpenMP, but that your implementation of threads is bad, and that you don't need heavyweight Unix processes to do this. So what we do in Argobots is have very lightweight threads so that even in OpenMP you could do over decomposition and work well. As David mentioned, these sort of things of stacking task graphs and threads together gives you that sort of flexibility of dynamic programming. Again, your program should be as static as possible, but there will be times when you have to start looking at dynamic behavior. And so There was a very nice list on David's slides. Charm++ is using, actually Sanjay Kale is part of this project. So they're building Charm++ on top of Argobots. There are a lot of these kind of lightweight layers that you should be exploring now and you should be exploring this week as well. Finally, I want to wrap up with another piece that adds to this dynamic behavior, and that is memory. So you might know that a couple days ago, Intel had an announcement that so it's really kind of funny. So for months, because we have a machine that's coming and we work with Intel closely, we're under NDA, and there are code names associated with all of the NDA things, before they're actually announced. So, you know that certain processors are named like, Ivy Bridge or Westmont or whatever. So there are names inside Intel, and then eventually, when they release the product, they come out with a marketing name. So the marketing name is this 3D Crosspoint Technology. And I don't know, can I say what the internal name was? Probably not. But we all knew it by another name. And so we were actually surprised, like, what, are they announcing something new? No, okay, that's what it is. So Intel and this, Micron is a company that is in Idaho. Is that where I think their headquarters are? Headquarters in Boise. And Micron is one of the, I think it is the last big memory manufacturer based in the United States. The design for their chips is based in the United States. And Intel and Micron have teamed together to create a new kind of memory that is 1,000 times faster than NAND. NAND is the standard flash that you have in your camera or even in my laptop. So this is a SSD laptop. So it is non-volatile, but it's 1,000 times faster in certain measurements, depends on how you look at it, than the standard NAND, right? So now this creates another tier in the memory hierarchy. So it's much faster than regular flash, still a bit slower than RAM, but cheaper in terms of how many bits you could store than RAM. So it lives in the middle here. So if you look at all of the places that we have memory, we now have some very interesting places to live. So we, of course, have cache, and then you heard today from James this word in package, right? So there's on die and there's in package. So the next chips from Intel will have memory that's in package and also have memory that's out of package, right? That's the standard DIMMs that you plug in. So now we have memory that's in package, and we have main RAM over here, and then we have this kind of technology that could also be out here, right outside the chip, right off the package. And then we have stuff that can even be further away, like regular flash and regular disk. So we have this very sophisticated and complex memory hierarchy. Right now, only in one place is it hidden from the user. So the cache is hidden. It's not addressable. I can't take a virtual memory address and store something directly into a cache. I assume that the machine, well, some architectures, I assume that the machine is essentially hiding that and doing that for me for free, right? Similarly, the only way to access these pieces is with a library call. So I write to disk using a file descriptor, or I write to NVRAM because it's mapped in some way, maybe to memory, but it's still through some sort of file descriptor. And in here, we still have sort of load store semantics. So now we have a very complex picture, and you should be thinking about this from your programs. So right now, how many different memory allocators do you have in your app? 4, 3. How many people call malloc? Right? Okay, then the system might allocate some things for you. You might be allocating some things. Do you really think about different pools that those data structures come from? Yeah. Do you imagine that, okay, well, there's some memory that's in package, and I might malloc from that part of memory, and then by hand move things from this part of memory to this part of memory, and then maybe again to this new piece to this part of memory. So this is a a real bleeding edge, because it's really painful to even imagine what our algorithms and what our code will look like as we try to wrestle with how do we represent, again, in our abstract machine, in our machine model, how do we represent this new memory hierarchy so that it's easy for the programmer. So in the end, I don't have to hand code all these little bits into my program, but I somehow declare something, a way to manage that. This is a very new area that we don't have much experience in yet. Yes, times are changing. We should be looking at embracing dynamic behavior in one form or another, understanding where in your code will things not be balanced. Optimizing for data movement, for imagining what multiple memory allocators will look like. This is the future for us. We will have in-package memory very shortly, in a couple years, on regular standard systems. Everyone should learn to love the runtime. You know, for a while, people really disliked the runtime. They wanted everything to be as, you know, as static as possible. And this is difficult because it makes debugging hard. It makes understanding what's really happening in your program hard. And it's no different than what's happening in the car that has sort of automatic power adjustment, right? There's a control system, and I can tinker with it, like move my foot to the accelerator and the gas and trying to figure out how it works. But in the end, there's a control system there. And that's how our future programs will be, with control systems that we have to reason about. Explore this adaptive learning as a way to understand how to optimize these things. And one of the things that we should do, this is just a commentary now, is that I see a lot of papers published where they will spend an entire postdoc or grad student where they run the code with one thread and 4 ranks, and then 4 threads and 2 ranks, and then you know, 2 threads and OpenCL and 4 threads and you know, this other compiler, and then they graph all these things. Well, you know, having that should be done by a computer or a script, right? And it should just pick which is the one to use, and it shouldn't be a paper. There's no new knowledge there. This comes out of just, you know, I tried this, and these two happen to work right now at an instant. There's no lasting insight there. So humans should not be in this loop of picking threads and ranks and compiler flags. That should be something that, I mean, we've done this before with Atlas and other things. And so if you see those papers, just toss them out, is my recommendation. So with that, I'll conclude, and we might have time for a question or two.
I would like you to share your thoughts about the low-level SIMD and SIMD-like and hardware threading parallelism, where, let me share my thought and then so I quite like the GPU-like multithreading, hardware multithreading, which gives the user the ability to focus in a simple way, just write the algorithm for one thread and focus. In the back of one's mind, there has to be a thought process of programming multiple threads, but all that stuff of over-decomposing and letting the hardware runtime, actually the hardware balance things and manage things through providing the means to be able to switch between threads.
Yeah.
That seems very elegant to me, as opposed to the classical SIMD way, which is hard and nasty, I think. And on the other end, there is SMT, which is heavyweight, very heavyweight, and it taxes the context, which is tax performance, and they are just a stopgap measure to kind of try to hide some latency imperfections. So, what is your thought on this, and why is this hardware threading not picked up more by new hardware vendors?
So I think, to answer the last part first, that we will see more interesting ways in which threads and work queues are integrated into the chip, right? Integrated into the way we run the system. So a simple example on Blue Gene Q was what Ray pointed out, the wake up thread. So the way the wake-up unit works on BlueGeneQ is that you can have a hardware thread that is blocked waiting for a memory write to a specific region. And so it doesn't have to be a message from another CPU, but it could be from anything. And so getting this very dynamic where the graph, the data graph, is actually almost represented in hardware threads on the machine is very nice. It's very attractive. But we're going to need thousands of those in order to really do the kind of graph, to do the sort of dynamic execution. Now, so we'll see more of those features. The reason we don't, it's not so convenient right now is that if the data structures and the computation you want to do is very regular, then some of these strategies work out quite nicely. However, if you want to do things that are not so regular, where a single instruction decode can't enable a large set of parallel operations to occur simultaneously, and that there isn't a nice queue of what to do next, it gets more complicated. It's not insurmountable, but it's complicated.
How is SIMD? How is the classical SIMD that Intel is pushing now the 512-bit better than the alternative?
So what Intel is doing is what they're attempting to do, and I shouldn't be speaking for them, right? Is that there's an engineering match between how wide and how many sort of heavier weight cores there are. And so picking that balance is one that has to do with what your instruction set mix and what your application mix is. You can turn that essentially all the way over to having a purely, lightweight data parallel machine, or you can turn it all the way over here and you have a cryogenic, machine that runs at 20 gigahertz. And there's an in-between, and the question is sort of at what levels and what will we see? And there was a question earlier, I think maybe you had asked it earlier today, which is, well, when will we get both? When will we get sort of bigger and smaller weight cores? And I think you heard from John's or James' note that he said it's a matter of time, right? So to save power, we are likely to have not just two, but maybe several stops in the complexity of the CPU, so that different kinds of things can be handled. And it may be programmable as well, like the FPGA approach. Another question? Yeah.
I have a question just to have your opinion on. So most of the codes that we work with or that we see are written, some of them in the 80s, others in the 90s, and it takes time before we start writing code, new codes that are used by everyone. And in a world where we have machines in multiple sites like Argonne, Oak Ridge, Japan, all different architectures, I'm not even talking yet about the Exascale that we don't know what it's going to be.
Right.
If we had to rewrite codes for different machines, we may have a portability in a few years, but performance portability, this is something that, according to this, is not going to happen any soon. But one way to go around it is to have the compilers do it for us, and basically having to write.
I think we all agree that we would love the compilers to do it for us.
So that's the question.
That's not a miracle
occurs.
But otherwise, that means that every few years we will have to write a specific code for a specific machine and manage it to have the specific architecture, reproduce whatever the machine was designed to do so. So the complexity comes back that it has to be managed at higher level.
So I agree. I wish that could be the case. I would say that the reason that the runtime system is and sort of more dynamic behavior is attractive to many users is that it's something that's in their control. So the compiler for most users is outside of their control. They can complain, they can send email, they can write, and then they wait and they hope that in the next revision minus 02 will vectorize the piece that they thought. And the runtime approach has other problems and complexities. But if you look at the work of Sanjay Kale, Charm++, other folks, it does do all of that work in user space. And with the right sort of exploration partner on the computer science side, you can get stuff done now, right? With lightweight threads, like with TBB and so forth. So there is something that, just from a development perspective, that's very attractive to that.
But it still means that it will have to be done.
Yes. Yeah, we'll be employed for a while. Yes.